All right. So welcome everyone once again to the set theory seminar. Our speaker today is Mohammad Golshani from the Institute for Research in Fundamental Sciences, and he will speak about the proper forcing axiom for Aleph one size posets and continue. Mohammad, it's great to have you here. Great to finally see what you look like. And go right ahead.
Okay, thank you very much for the invitation and giving me give me a chance to give a talk for your seminars. My talk, as you said, is about PFA for forcing notions of size Aleph1 and the continuum hypothesis, and this is based on a joint work with David Aspero. So I assume everyone knows what is a proper forcing, but just maybe I just for start, just give as a definition that there is a forcing notion P is called proper if for any large enough regular cardinal theta and for every countable elementary submodel of H theta, when M contains enough information, for example, P is in M, and for any condition P, which is in P intersection M, we can find a condition extending P like Q, which is such that Q is MP-generic. And MP-generic just means every dense subset of P, which is in M, is pre-dense below Q. The proper forcing axiom just states that, maybe just PFA, it says that if P is proper and we have a collection of Aleph1 many dense subsets of P, then we can find a generic filter which meets all these sets VI. If there exists a filter G meeting all VIs. And by the work of Baumgartner and Schiller, we know that PFA is consistent modulo the existence of a supercompact cardinal, and it is a result of Todorchevich and Veliskovich that PFA implies the continuum is just Aleph2. Also, it is a theorem of Schiller that one can force PFA for forcing notions of size Aleph1 without using any large cardinals. Of course, the proof is easy. It's just a countable support iteration of length Aleph2 of forcing notion, where at each step we take one proper forcing of size Aleph1, and by bookkeeping we can take all of them. But there is one important point in the proof, and it's to show that this forcing has enough nice properties. For example, it doesn't collapse cardinals. And for this, Schiller uses the concept of peak properness isomorphic condition that guarantees that the forcing is well behaved. And since I need it maybe I just give an idea of what is this concept. So definition, I'm not going all the details, so maybe just P is peak. As I say, it's just properness, isomorphism condition. If for any large enough theta, and for any two models, N0, N1, elementary submodels of H theta, which contain enough information, for example, P's and then, if we assume they are isomorphic, and say pi is an isomorphism from N0 into N1, and they have there is some extra properties, for example, N0 intersect N1 intersect omega 2 is an initial segment of both of N0 intersect omega 2 and N1 intersect omega 2, and one extra property which says that N0 intersect omega 2 is a subset of N1 intersect omega 2 minus N0, and for any condition P which is in N0 intersection P, we can find Q extending P where Q is N0 P generic. And this is very important. Q forces for any condition R is in G dot of P if and only if pi of R is in G dot. And there is one extra property. Excuse me. Of course, I think this is enough. Q forces P is in G dot. Of course, this is clear. At least if the forcing is separated. Now, the concept of peak is important for this result of Scheller. Let P alpha less or equal delta and Q dot beta less than delta be a countable support iteration of peak forcing notions. Then we have two properties. First, if delta is less than omega 1, omega 2, so if delta is less than omega 2, then P delta is peak. If delta is omega 2, P delta is Aleph 2cc. So this is very important just for Scheller to show that his forcing iteration satisfies the Aleph 2 chain condition. And another important property is if CH holds and delta is less than omega 2, then P delta preserves CH. It shows that during the iteration before the last step, we always have CH in the iteration. Now the natural question comes that, and it is asked, for example, by Scheller, I see, can we have, does PFA for forcing notions of size Aleph1 decide the continuum? And the answer is no, and I would like to discuss this result. So the main theorem that I would like to state here, so this is joint work with Aspero. I want to show that give for any regular kappa, like say Aleph 3, because Aleph 4 follows from Scheller's result. There exists a proper and Aleph 2cc extension Oh, okay, I assume GCH in the ground model extension in which 2 to the aleph 0 is kappa and PFA for forcing notions of size aleph 1 force. The proof uses Shell's memory iteration. It was introduced by Shella in the context of final support iterations. Then in a work with Shella, we defined a version of it, which was a mixed support iteration, both finite and countable. And in this work with Aspero, we introduced this. And here I would we introduce a countable support iteration of this memory support iteration. So I would like to say I think the proof gives also what is the memory iteration. First, I may say that the natural countable support iteration doesn't work because it always collapses the continuum to aleph 1 if the length of the iteration is about aleph 2. So I will make this. So I would like to say how to prove it. I will skip many details, maybe just to make it simpler to understand. The idea of the proof is something like this. We do an iteration of length kappa. It is very similar to the countable support iteration. So each condition will have a countable support. But the point is that, in the natural iteration, when we are at step alpha and we want to define our next forcing notion Q alpha is a name for P alpha. But here we would like Q alpha just to be a name for a subset of alpha of size at most aleph 1. This is called the memory. So a first thing, I have something P alpha, Q beta dot, I have some memory U beta, and mu beta, of course, mu beta is not really important. Mu beta is just the cardinal where Q dot of beta, I assume, is of the form mu beta and some relation on it. So it's not really important to introduce it, but U betas are very important. They are memory. And simply they say that Q dot beta is a U P U beta. I will introduce U beta name. In some sense, Q dot beta only depends on aleph 1 many ordinals. So as I said, mu beta, because I want just to forcing notions of size at most aleph 1, so mu beta is just a cardinal at most aleph 1. Or it's just aleph 0 or aleph 1. U beta, as I said, is a memory. It's a subset of beta of size at most aleph 1. For some reasons that will become clear later, we assume these U betas are in some sense closed, in the sense that if SI is U beta, then U psi is a subset of U beta. So, assuming I have defined P alpha, I can define P U beta as the conditions P, such that domain of P is a subset of U beta. And I want, indeed, it will And indeed, we will see it is a complete suborder of. Do you hear me?
Yes,
Okay.
yeah, the
It
sound
is
is good.
Okay. It is a complete suborder of P. But the main point is this condition, Q beta dot. It is not a P beta name. It is just a P U beta name for a forcing notion. And I assume that it is forced by this PU beta that Q dot of beta is just mu beta and some order on it. And maybe now we can say, of course, if the forcing is Aleph to CC and Q beta is P beta name for some subset of size Aleph 1, it should be PU beta name. But the point is here, finally, we say P is in P alpha if and only if P is a function with countable domain. And the main point is for any beta in domain of P, in the natural countable support iteration, we assume P restricted to beta versus P beta is in Q dot beta. But here we assume P restricted to U beta versus P beta is in Q dot of beta. And this is the main difference between countable support iteration and this memory iteration. Okay, this is
Mohammad?
essentially the,
Mohammad?
yes.
So these
Yes.
U betas are actual sets of ordinals. They are not names for sets of ordinals or something like that.
Which one? U beta, yes, it's just the actual set.
Oh, okay, all right.
Because you will see the forcing notion is Aleph 2CC at the end. So any set of size Aleph 1 at the final extension is covered by one from the ground. That's why you just need the actual sets.
Okay.
And the extension is the natural one. So the main difference, as you see, is that is this last condition of that Q of betas just depend on a set of size atmos Aleph 1. Okay, I don't write the order because it's just a natural one. And what I would like to show this forcing, okay, if I show it is proper and it satisfies the Aleph 2 chain condition, then by just a bookkeeping argument, I can ensure that all forcing notions, all proper forcing notions of size Aleph 1 are considered, and during the iteration, I can iterate the Cohen forcing kappa many times, so I will get 2 to the Aleph 0 is kappa and PFA for forcing notions of size Aleph. So there are two things just to prove. First, P is proper, and two is to show that P satisfies the Aleph 2CC. The proof of properness is very similar to the proof that the countable support iteration of the forcing proper forcing notions is proper. Excuse me, I forgot just to say one thing. Okay, in the definition of forcing, I should add one more requirement, and that's otherwise I can't prove the forcing is proper. And it's to show I can assume that not only PU beta forces Q dot of beta is proper, I assume P beta forces Q dot of beta is proper. This is also this is very important to show that the forcing remains proper. That I forgot to say. So the proof of properness is, as I said, just similar to the proof that continuous optimization of the proper forcing motion is proper. At limit stated, the proof is the same. So I just sketch a proof for successor case, because the forcing as successor case is a bit different. But the point is that we have a very natural projection from P beta into PU beta, yes, which sends any condition P into its restriction to U beta. And this induces a projection from VP beta into VPU beta. Very natural projection. This is a projection. And I can define a projection from P beta star Q beta. Note that Q dot beta is a PU beta name, but PU beta is a complex suborder of P beta. So I can define this as two-step iteration, and any condition here, I send it to P restricted to beta and pi beta of P beta. I can show that this is a projection. But note that by induction, I assume P beta is proper, and one of the main concerns was that P beta forces Q dot beta is proper, so this is proper, and P beta 1 is just the projection of a proper forcing motion, so it is proper. And this gives of course, note that P beta plus 1 is not P beta is Q beta of beta. The second thing that remains to prove is to show that P satisfies the Aleph 2 CC. And this is the main advantage of this forcing with respect to the countable support iteration, because we know at the case of countable support iteration, it is not Aleph 2 CC if we go above Aleph 2. And for this, we need some lemmas, which are indeed easy. The first remark is okay, maybe I just give a definition first. Suppose A is a subset of kappa, we say A is U closed if for any QC is in U, UQC is a subset of U. The point is that if U is, excellent, if A subset of kappa is U closed, then we can define PU exactly as before.
Mohammad? Sorry.
Yes.
What you denote by U, that's the function that maps Xi to UXi? Is that what you mean?
No. Just this is, I say a set A, which is a subset of kappa, is U closed.
Yes.
If it has this property, that if QC is in U, then U of QC also is a subset of U.
And what is U?
UQC is, oh, excuse me, this is A. Oh,
that's A.
This is
yes.
A, sorry.
Okay.
Oh,
that's
yes,
what I thought.
A.
Okay.
Oh, yes, that's A. Excuse me.
And so for all Xi in A, UXi is again in the last
QC
line.
Is in A, yes. Excuse
okay.
me. Sorry.
All right.
You're right. If QC is in A, then
okay.
QC is in A. And if A is U closed, then we can define the forcing. So this should be PA. And the point is that PA is a well-defined forcing notion, because any component which is relevant appears in A itself. And now it is easy to show that if A is U closed, indeed PA is a complete suborder of P couple for P. And this is of course true for any alpha. If A is a subset of alpha and it's U closed, it is a complete suborder of P alpha. And it's quite easy, just like iteration. And the second lemma, which is maybe interesting, if A subset of kappa is U closed and size of A is at most aleph 1, then PA satisfies the aleph 2 CC. And this is like Shell's theorem that says if the countable support iteration of peak forcing notions of length less than aleph 2 is peak and hence aleph 2 CC. And here size of A is at most aleph 1. So if you order it, it has some order type less than aleph 2. And a similar argument shows that PA satisfies the aleph 2 CC. And having these two lemmas, we can easily show that P kappa is aleph 2 CC. And the proof is indeed easy, because suppose we have some conditions Pi, I less than omega 2. Suppose we are given aleph 2 many conditions in P kappa. So for any I less than omega 2, we can pick some AI, which is U closed, and PI is indeed in PAI. Because the support is countable, yes. And we can assume AIs are increasing. I less than J less than omega 2 implies AI is a subset. It's sufficient to define the AIs by induction. Now let A be the union of AIs, I less than omega 2. So this is U closed and a subset of kappa of size aleph 2. Furthermore, the point is that all conditions Pi, I less than omega 2 are in PA. I called it AS. So all these conditions are in PA. But now, look, I assume GCH, in particular CH in the grand model. And PIs have countable support. So by a delta system lemma, we can assume the set of domain of PIs, I less than omega 2, form a delta system with say root, say D. Yes, but D is countable. So for some I less than omega 2, D is in, maybe for some QC less than omega 2, D is a subset of A QC, yes. And since I have omega 2 many sets, we can also assume excuse me, these sets have this property that actually their complement is outside of AQC. I mean, domain of PI minus D intersect AXC is empty. Now it is easy to see okay, no, we are not still at the end. Now look at the sequence PI restricted to AXC. This is a subset of PAXI. And by the previous lemma, we know this satisfies the Aleph2CC. So there are some I less than J less than omega 2 such that PI restricted to AXI is compatible with PJ restricted to AXI. And now it's easy to see PI and PJ are compatible. But that they are disjoint. Have to see it. Up to AKC, more or less, they are the same. They have a common extension, and outside of AKC, they have disjoint domain. So just amalgamate them to get a condition. And this gives the proof. And as I said, just by bookkeeping argument, now I can conclude that. Maybe I just say, did it? Maybe,
Mohammad, can I ask you a question? So you just said that this lemma that PA essentially is omega 2 CC, that the argument for that is similar to Philar's argument using the pick. But you don't have anything like the pick in the definition. So what's the replacement for what makes this argument work if you don't have?
If CH hold and forcing is of size Aleph1, it satisfies pick. Okay, and here we are forcing just by forcing notions of size Aleph1. So they satisfy pick.
I see. Okay,
that's the point.
Okay, all right. Okay, thank you.
Do you want I say how this bookkeeping argument works, or I see it's clear? Yes.
Sure. Why don't you give us some idea?
Okay, I will give them. Now I claim that, as I said, suppose by bookkeeping argument we have taken all forcing notions of size Aleph1. Now for example, Q. Let work in P couple. I want to show that PFA for forcing notion of size Aleph1 works. Let Q dot be a PA couple name for a forcing notion of size Aleph1, which is proper. So we have a proper forcing notion of size Aleph1, and suppose we are given D dot I less than omega 1, Q dot names for dense subsets of P. Subsets of Q dot. So I assume kappa is a regular cardinal greater or equal to Aleph3. So I can find some, and the forcing, note that the forcing is of size Aleph1. I have Aleph1 many names for dense sets, so I can find some beta less than kappa such that Q dot is a P beta name. Also, the I's, D dot of I. Yes, but again, I can find a subset of beta of size atmos Aleph1 again by Aleph2 chain condition. such that all of Q dot and BI dot for I less than omega 1 are P, maybe I call it A. I can find set A, they are PA names. And I can assume that A is U closed. Just enlarge it. Now, during the iteration, I can, as I said, by bookkeeping, I can assume that just for some, by our bookkeeping, I can assume we can find some beta prime greater or equal to beta, that Q dot of beta prime and mu beta is just is Q dot. And mu dot is just the size of this force solution. Yes. So at step beta, we are forcing with Q dot of beta. And all the I's are also appearing there. Actually, I may also say U beta is also this A. So at step beta prime, at the step beta prime, we are essentially forcing with this Q. So we are adding a generic for it, which meets all the I's, and this gives the proof. And just maybe the next natural question is, what about forcing notions of size Aleph2? I don't know. Even for forcing notions of size Aleph2, which are Aleph2 CC or even Aleph2 peak, I don't know. The argument doesn't work, and I have no idea if we can prove a similar result or not. Excuse me. I'm finished. So if you have questions or
well, thank you.
You're welcome.
Yeah, I don't know. Does anybody else have questions for Mohammad? I guess I would have a question. So you could, of course, ask what happens if you go up one cardinal, but you could also ask what happens with other forcing classes than proper. Is there a version of this pick for wider forcing classes, like semi-proper or something like that?
I think Shella defines kappa pick in general, and the same results work for kappa. But for example, if you force us with forcing notions which are of size Aleph2, for example.
I understood that, but my question was, rather than changing the cardinal, changing the forcing class, so replacing proper with something else. Is there a version of pick, say the semi-proper isomorphism condition or something like that?
I don't know.
Okay. Okay, any other questions? Okay, I think everybody seems to be satisfied. Well, thanks a lot. I thought it was a great talk. Very nice. Almost like sitting at a table and you're writing on a sheet of paper explaining this. Very nice.
Yeah, Mohammad, thank you. Thanks very much.
Thank you very much. Thank you for the invitation. Bye.